Welcome everyone. So, um, this is our first online meeting, and let me introduce about our team, and then we will go about this tutorial. A brief introduction about this tutorial, and then I will hand over to the Mark to do the presentations and of tutorials. So we are the young Indian astronomers, which are currently involved in different universities and the research institutes doing postdocs and PhDs and other like faculty jobs and all. So basically, we are the team from Indian origin and currently pursuing different kind of jobs at different institutes in the world. So we thought that okay, so since we are working in astronomy and in astronomy, the catalogs are very important to deal with, and we while doing the PhD, I faced uh, problem while dealing with catalogs, astronomical catalogs. But thanks to Mark Taylor, who developed this software TOPCAT, which is just a visual interactive platform where we can deal with astronomical tables and all. And I'm using it since last 10 years, this softwares. I mean, since 2018, so it would be around 8 years. Okay. So last 8 years, I am using this software, and it is. I say that it has quite rich catalogs and archives and very smooth technique to deal with. And we thought that okay, so since most of the in Indian universities we use this tool, some people who are in early PhD, so they definitely need to know that. So okay, so by their seniors that okay, so TopCat is one of the software. So we thought that let's request the developer of the software, who is Mark Taylor, and request him to give a tutorial to us so that the early and the advanced level people who are using TopCat, they can get the benefit. So let me introduce it to about the Mark Tiller. Mark Tiller is a researcher at the University of Bristol in UK, and he has developed it quite vast I mean online techniques to deal with within the TopCat. Stilts is one of them, so where you can use it and. In detail, I think that we will get uh, about this TopCat and its uses to the different archives, astronomical archives here. And let's thank Mark to agreeing for give this presentation. And I'm going to hand over this session to Mark to guide us through this. Thank you, Mark. So please
Great.
start your presentation.
Okay. Thank you very much, Ranjan. And it's a pleasure to give a talk to this community. So yeah, I'm going to talk about TopCat, and this will be kind of partly an introduction and partly a tutorial about how to use it. I've put on this first slide a link to a place where I've got presentation materials. So if you want to go there just for reference, that's got the slides that I'm going to give now and the tutorial script that I'll go through later, plus some of the data files that can be downloaded if for some reason the services aren't working. So you can refer to that if you like. Oops. Okay, so the structure of this talk will be I'll give about a half-hour talk just explaining what TopCat is and what it can do without assuming any prior knowledge of that sort of thing, just so you have an idea of the kinds of capabilities it's got. And then most of the talk will be live demonstrations using TopCat and working mostly with data from the GAIA astrometry mission. So I'll give a little introduction to what GAIA is just before I start off on the demos for context. And that will hands-on thing will last for I don't know, maybe an hour or so, and I'll go through the examples, and then you can either follow along or just watch what I'm doing, and there'll be some gaps in between. I'll talk about that more when I get there. I'm quite happy to answer questions. It probably makes sense to do that in the gaps between the examples and the gaps after this introductory half hour. But if you've got any questions, then please post them and someone will bring them to my attention. Okay, so TOPCAT is a desktop tool for working with tabular data, and mostly that means source catalogs, but it can be other kinds of tables as well. Uh, and it can do it's supposed to work for everything from if you've got a table and you don't know what's there and you just want to kind of take a look at it and see what kinds of columns it's got and what kind of rows, and just do very simple visualizations of it, see where the points are on the sky, that sort of thing, all the way to trying to squeeze all the interesting scientific meaning that you can out of the data that's in there by manipulating the rows and looking at projections and different parameter spaces and all sorts of things. And its basic aim is to do all the kind of boring mechanical things that that astronomers need to do while they're working with source catalogs and other tables. And that means things like getting data from different file formats, getting data from external services, doing visualizations, doing cross matches, moving columns around, keeping track of selections of rows and tables, so that when you're using it, you don't have to concentrate on all that kind of boring, laborious stuff of wrangling numbers from one place to the other. You can concentrate as the astronomer on really thinking about the science and the astronomy rather than the details of how to move numbers around. So these are what I hope it is. I guess it's for you to judge whether this is really true. It's supposed to be user friendly, so hopefully it's easy to install. I gave some installation instructions earlier on, and I'll go through that very briefly later if you haven't done it by now. I guess we won't have time to go through that in detail here, but it should be fairly easy to download and install. You don't need to worry about lots of different library issues because really you just need Java plus one file. So as long as you've got Java installed, it should be okay. And it's supposed to be easy to get started working with it. So if you've got a table, you can point the software at a table, and then just by clicking a couple of buttons, you can see what data's in there. You can do a few plots on it. So simple things should be fairly obvious to do, plotting sky positions, doing basic plots. It can do much more complicated things which aren't so simple to do, and once you get used to it, you can hopefully play around with it, click some buttons that you haven't seen before and see what happens, look in the documentation. So you can hopefully interact with it at whatever level is comfortable for you. If you just want to do very basic analysis, then you shouldn't have to work too hard. If you want to do more complicated analysis, then you might have to work a little bit harder. The complicated things are at least well documented. There is a big fat user manual, which you can engage with in various ways. You can click the help buttons on the windows, which will take you to the right part in the manual, or you can look at the manual online. There's a big HTML document, or read it in as much detail as you like. But pretty much everything it does is actually written down in the documentation. It's quite high performance, so most things that you want to do, you shouldn't be, clicking a button and waiting a long time for things to happen, even for quite large tables. So by large tables, I mean millions, maybe tens of millions of rows and hundreds of columns. And for that, you don't need to have a big fat computer. Pretty much any laptop or desktop that you're sitting in front of should be able to work. Do visualizations and scroll around the data and do cross matches and so on with tables of that sort of size. And the whole point of it is to do things that astronomers need to do with this kind of data. I started off writing it 20 something years ago, and it just did, it could just display the contents of a table, and a few people looked at it and said, oh, that's quite nice, but it'd be nice if it did this as well, did some cross matching, did some visualization. And so all the things that I've added onto it over the last 20 years, which is much longer than I was expecting to be working on it, have really come from engaging with astronomers, getting feedback from the community, people saying it would be nice if it did this, or why can't I do that, or this doesn't work like I'd expect it to. And so me taking that input and folding it into the current capabilities. So you as a user community are really important to the way it develops. And I'm always interested in feedback of whatever kind from people who are using it. Okay, so I'll just go through a brief list of the sort of things it can do here, and then the next few slides I'll go through those in a bit more detail. It can read and write tables in various formats that are kind of useful to astronomers. It can look at data and metadata of the tables that it's looking at. It can do calculations, and it has an expression language so that you can combine columns in various different ways. Lots of different sorts of visualization options. You can make row selections and keep track of which subpopulations of a particular catalog behave in different ways and appear in different parameter spaces. Lots of ways to do cross-matching. You can talk to external data services. I'll talk about the virtual observatory, which is something that you might or might not have heard of, but that's underlies some of the ways that you can get data from external services. It can talk to other tools on the desktop, so DS9 and Aladdin and some web applications as well. It can communicate directly with, and you can do things like click on a point or click on a row, and it will cause interesting things to happen if you've configured it to do that. Worth mentioning what it can't do as well. So it's a table manipulation tool. Don't try and load an image into it. That won't work. It doesn't understand images and doesn't try to. And other data types as well. It's not designed for use with spectra. Spectra, depending on how they're serialized, might look like a table, and so you might be able to load a spectrum into it if it's got, a column indicating frequency and a column indicating flux or something like that. So you might get some way of doing that, but it hasn't got, for instance, sophisticated spectral functionality built into it, so don't expect it to be good at that sort of thing. You can't script it directly. It's a graphical application, a GUI application, so it's just for pointing and clicking really. I'll mention later on briefly Stilts, which does provide a scriptable interface to some of the same capabilities, but TOPCAT application itself you can't script. There is a limit to the size of tables it will work with, so you can't point it at a billion row catalog, sort of the size of TOMAS or GAIA source catalog. But as I say, some numbers of millions of rows is okay. There are some formats, file formats that it doesn't work with. It doesn't cover absolutely everything, but it does quite a few of the useful ones. And importantly, it's not going to do your astronomy for you. So it won't write your papers. It won't do scientific reasoning. It gives you the tools to do that for yourself. It's actually pretty low level in an astronomical sense. It doesn't understand what a galaxy is. It doesn't know about galactic dynamics, and there's no kind of AI functionality in there at all. But it gives you the tools for you to be able to move the data around and look with your with your understanding to work out what's going on with that data. Okay, so I'll go through the different capabilities in a bit more detail. First, most obvious thing that you can do when you've loaded a table in is to look at table data and table metadata. So there's a window like this which shows you the columns and rows of the data that you're looking at. But importantly, you can see the metadata as well. Now, metadata is, information about the data. And if what you've got is a 3-column CSV file that you've just written yourself, then the metadata is not very interesting because you know what's there. But if what you've got is a catalog that you've downloaded from a remote service with some sort of complex data in it that you haven't seen before, then you really need to know information about that data before you can make any sense of it. So for instance, this window here, you'll probably end up using is the table columns window. So once you've loaded a table, it will tell you about each of the columns in that table. So it gives you the column name, obviously, and the data type, the units of the column, which is obviously really important. You need to know, if you're looking at a extent value, whether it's in arc seconds or milli-arc seconds or degrees or whatever it is. Otherwise, you can't make sense of it. And depending on how the person or the organization who's prepared that table has gone about it, there might be some sort of human readable information, a description of the data per column or whatever it is. And then there's also some per table metadata as well, which might say, for instance, what the query was that you wrote in order to get it back, or who authored the table, or what instruments it came from, or what some associated papers published with it are. So that can be useful as well. A lot of the analysis that it lets you do has to do with making row selections. So typically, if you're looking at a source catalog, there's all kinds of different things in there. There might be stars and galaxies. There might be different populations in different clusters, different parts of the sky, whatever it is. And a lot of astronomical analysis comes down to, at least of catalogs, comes down to looking at the contents of a catalog and trying to split it into different subsets of rows, different subsets of sources, to work out which ones are like which other ones, which are outliers, and kind of what you can infer about the astronomy that's going on, the astrophysics from the subpopulations that are there. So TOPCAT gives you lots of tools to do that. The basic thing is what it calls a row subset, which is just a selection of rows. And so you can have multiple subsets maintained within a single table. One of the most straightforward ways to do it is you can do a plot, and then you can just draw a kind of blob around the points that you're interested in, and then they become a subset, and you can manipulate those separately from other subsets in the table or from the background objects. You can also define subsets using algebraic expressions. I'll show you about that in a minute. If you've got multiple subsets, you can say we can have the intersection or the union of these or whatever it is. And you can also use other applications like Aladdin or something to identify objects that you're interested in, and then transmit that information, those subsets, to TOPCAT to work within there. And once you define one of these subsets in one plot, then the same information, the same subset, is visible in other plots which has got the same data. So a lot of the time what you're doing is identifying points using a region in one parameter space and then seeing what that selection of points looks like in another parameter space. And linked views is a sort of graphics buzzword that says what's going on there. If what you're interested in is not so much a population of points, but a single object, a single source in your catalog, then there's ways to work with that as well. So again, with this linked views thing, if you've got any kind of plot and you click on one point, so here I've clicked on this outlier here in this sort of color magnitude plot, and then I can see where that same point appears in another plot, which is done in a completely different parameter space, some sort of a 3D plot here. So these are the same objects, and at the same time, if you've got the table viewer window open, the row that it corresponds to is highlighted there, and then you can configure lots of different things to happen as well if you click those points. For instance, in this case, I've got another application open, Aladdin, which is an all-sky viewer with some 2-mass imagery, and so when I click on this, it tells Aladdin, can you point to this point's position in the sky? And so you can actually see the imagery corresponding to these as well. So you can find out lots of information about single objects just by clicking on them. It's quite straightforward to do. I mentioned doing calculations. So you often want to do calculations on columns. For instance, you might have a table which has got a U magnitude and a G magnitude, and what you want to know is the color, the difference between those two magnitudes. And so you can use the expression language in TOPCAT to create a new column, which is that difference. And it's just as if that column U minus G was in the table in the first place. And when you save it, you can save those values. So the syntax for doing that is it's actually Java syntax, which it's also like syntax in the C programming language, but it for most purposes just looks like the kind of thing you'd expect from writing variables and operators and functions and things like that. So here's an example. If my columns in if I've got a column called mag U and mag G, then I can just open a window saying, please, can you give me a new column? And I just type in mag U minus mag G and give it a column name, and then it creates a new column based on that. So that's what the syntax looks like. And you've got the standard arithmetic operators, plus, minus, divide by, times. There's standard kind of mathematical functions as well, like trigonometric functions and minimum, maximum, things like that. You can do conditional expressions as well using this ternary operator that you might be familiar with. Manipulations on sky coordinates. So if you've got columns which represent two different positions on the sky, you can calculate the distance between them in degrees. Various things for working out if you've got proper motions, you can work out where an object is going to be in 10 years' time based on its current proper motion, its current positions. Conversion between fluxes and magnitudes, and a bunch of other things as well. So there's quite a wide variety of things you can do, and it's easy to calculate these new values from the values that you've already got. And there's another couple of examples down here. So if you've got a brightness in flux, you can create the value in magnitudes just by using this expression Jansky to AB, and this was the one that calculates the distance between an RA in a deck and another RA in a deck in degrees. So this expression says it's a Boolean expression, true, false, and so you can define a subset of rows by saying if this expression is true, if the distance between the RA and the deck of the source that I'm looking at is within 1.2 degrees of this position that I've given it, then it's in the selection, and if not, it's out of the selection. So that's another way you can do row selections. Visualization, there's lots of visualization options in TOPCAT. Plots in 2D and 3D and histograms and all sorts of things. I won't go through them all. But there's lots and lots of different options. They're highly responsive, so you do a plot, and the way it works is, so if you look at the details of the plot windows, there's a lot of controls and sliders and checkboxes and so on there, and it kind of looks complicated to work with. But the idea is, if you just push the button saying "Can I have a scatter plot?" it gives you a scatter plot of a couple of columns that it thinks you might like to be looking at. And then if you don't like that, you can choose different columns pretty easily. And if you don't like the color scheme, you can play around and find the control that changes the color scheme. So for an easy plot, if you don't really care that much what it looks like, it's easy to get it. And if you want to go digging and configure it much more carefully, then you can do by looking at the documentation, or often just playing around with the controls that you can see. It tries hard to work well with large data sets. I mean, it works perfectly well with small data sets as well. You can do, interesting and useful plots with 20 points. But if you've got 1,000,000 points, it tries to do a good job of that as well. And there's a few aspects to that. One is you don't need a lot of memory to do plots for very large data sets. It tries to do plots that you can make sense of with lots and lots of points. And I'll do another slide about that in a minute. And if you've got lots of columns, if you've got high dimensional data, because you've got a table with 100 columns and you don't know which ones are interesting, then it tries to give you various options for understanding that as well, by doing lots of plots at once. You can do a corner plot, or by coding the different points by color or by size or shape based on additional quantities and so on. It does do publication quality output, so you can do plots and output them directly to something that you can put in a publication paper if you want. It's probably fair to say it's not quite as flexible or beautiful as, say, Matplotlib or R for that sort of thing, but some people use it for publication graphics. A lot of people, what they do, I think, is use TOPCAT to kind of work with data and play around with it and explore it, which is what it's really good at. And once they've worked out what it is they want to do, once they've worked out what the plot is that they want to present, then they might take that data and put it into Python and do a more carefully generated plot using Matplotlib. But you can choose how you do it. Okay, that's just a selection of some of the kinds of plots that you can do. So you can do scatter plots, that's an all sky plot, histograms. That's a 3D plot, and in this case, you've got little vectors pointing around there. Some sort of spectrogram. That's a sky plot of density in what might be Magellanic Cloud, I'm not sure. It can do shapes and corner plots like this. All right, so I was talking about dense plots. So the problem is if you've got, say, 5 million sources and you want to plot them on a 500 pixel by 500 pixel window, then you're going to lose some information if you do it in a straightforward way, just because there's more points than there are pixels. So if all you do is just color in a pixel wherever there's a data point, then you'll end up with something like this, where you can see kind of sort of what region of space it's covering. But there's structure in here that you can't see just because lots of points are piled up on top of each other. So TOPCAT gives you multiple different ways of doing the plots so that you can try and understand that structure in better ways. You can do plots with transparency, which helps a little bit because then you can see where there's, you know, kind of low density regions and high density regions, but you still kind of lose a bit of information here. And when there's low density regions, you can't really see the outliers so well. You can do contour plots, which is sometimes a good way to do it. You can do a grid plot where it just chops the parameter space up into bins in 2 dimensions and colors each bin according to how many points are sat on top of that bin. But the ones that are kind of easiest to use and most often used in TOPCAT are these two, density and auto. So if you just do a plot straight away, what you get is this auto plot. And what that does is when low density regions, so if you've just got an outlier, it looks exactly like a you know, kind of standard plot like this, where you just draw a dot where you've got a point appearing. But where you've got lots of them piled up on top of each other, it makes them darker. And so it's pretty easy to see from here, okay, so there's some outliers here, and then lots of them around here, and then here, this is where most of the points are piled up. If you want to do something like that, but have a bit more control over it, there's the density option. And in density option, you can control what the color map is and how the color map changes according to how many points you've got, what kind of scaling there is, and all sorts of things as well. So these two are often useful if you've got large amounts of data in a plot. Cross matching is another thing that's important. So that's where you've got, for instance, two source catalogs, and you want to know which sources in one catalog correspond to which sources in another catalog. And there's various different ways you can do it within TOPCAT, depending a bit on how big those files are that you want to match. The most straightforward one is if you've loaded, it doesn't have to be two, it could be one or it could be more, but say two catalogs directly into TOPCAT. If they're, you know, a reasonable size and you've loaded them in, then there's this match window here, which is quite straightforward to use. So you just say, okay, I want to match on sky position, or there's other things you can do as well. You can have errors that might be provided per object in the input file, or you might want to match on position and magnitude as well. But in the simplest case, you just say, okay, I want to match on sky position, and then you tell it what's the largest distance you're prepared to tolerate between a source in one catalog and a source in the other catalog. And you tell it what catalogs you want to match and tell it which are the position columns, and then hit go, and it'll go off and tell you what the associations are between the two catalogs, and sometimes it will plot that for you as well. So here you can see this pink source has been identified as being the same thing according to this matching criterion as this cyan source. So it's pretty fast. It usually happens just, you know, kind of while you wait. If you've got large catalogs, it can take a couple of minutes maybe, but usually you don't have to wait that long. And there's quite a lot of options for doing it. If what you want to do is match against a very large catalog, so you know you've got your own catalog of 1,000 sources, but you want to see which of those exist in, say, the 2MAS catalog or Allwise, or something that exists on a remote server, but it's too large to download in its entirety. There's ways of doing that as well, and I will go through some of those later. But basically, they work by taking the table that you've loaded into TOPCAT, sending it to a remote service. The remote service does the matching and then sends you back the results. So there's various options for being able to do that too. Virtual observatory is a buzzword you might have heard of. What it is the infrastructure that makes it possible to work with data from remote archives in astronomy, and it's quite well advanced. It's been it's somewhat invisible infrastructure, but it's what often is makes stuff work when you're trying to get data from remote archives. And you can think of it a bit like the World Wide Web. So if the World Wide Web is a bit like having all the all the documents in the world that are sitting on your computer, so you can look at them. The virtual observatory is a bit like having all astronomy archives in the world sat on your computer, so you can work with that data. So what it's not is one big computer somewhere with a load of data that you can ask it for anything that you want, and you get it from that computer. What it is a set of protocols and standards and infrastructure and bits of software that can talk to each other in a uniform way. So that if TopCat wants to ask, have you got sources in a given position of the sky? It can ask it in the same way to lots of different services and get results back in a way that it can understand. So in most cases, if you're using TopCat, it hides those details from you. You don't need to understand what's going on really, but it can help to have a rough idea of kind of the operations that are happening under the hood. TopCat is quite well embedded into the virtual observatory. It has interfaces for lots of the different VO capabilities, and that includes cone search. We'll see that in a minute, which is just where you ask for sources from or rows from a catalogue in a particular region of the sky. Table access protocol is much more complicated, and that's where you make SQL-like queries against remote databases, and it's very flexible, but it takes a bit more effort to use. And again, TopCat gives you help with that. Simple image and simple spectral access are a bit like cone search, but instead of asking for rows from a catalogue, you're asking for images or spectra from data sets that have that information in them. The registry is the directory of what services are available with what data in them. So if you want to go and do a cone search, what you do is ask the registry, okay, can you tell me a cone search service which has got information on this particular data set that I'm interested in. SAMP allows TopCat to talk to other tools on the desktop. So for instance, Aladdin or DS9 or web applications. And as well as these ones, which are VO, there are some services provided by the data center in Strasbourg, CDS, which do lots of useful things. They're not strictly VO services, but they're talking to external services, which can do useful things for you, like, for instance, name resolution and cross-matching. Okay, I'm not going to talk very much about stilts today, but I'll just mention it so that you know it's there. What stilts is a command line interface to pretty much the same capabilities that TopCat has. So they're both built on the same software infrastructure, and they're two different user interfaces to it. So TopCat is the GUI interface. You point and click on windows, and stilts you write command lines in the shell or some other kind of way of providing imperative commands. And so then you can write scripts and you can make them reproducible. And you might never use stilts, or you might like to use stilts. It depends how you like to work. But typically people use TopCat when they're exploring data, trying to work out what's there, trying to understand it. And don't have a particularly clear idea of exactly what they want to do with it. But if, for instance, you've worked out what you want to do with a table with TopCat, and then you need to do the same thing on another 100 tables, it's a bit boring to keep pointing and clicking the same way 100 ways. So then you can codify it and write it in a script and apply stilts to it and put it in a loop or whatever you want to do. So as I say, I won't talk much about stilts, but you can go to the documentation, find out about that if you want to do some of the same things that TopCat can do, but you want to be able to script them. So this is just a page on installation. Hopefully, if you want to install TopCat, you will have done that already. If not, you can go back to this and see how it is. What you should really do is go to this link here, which is on the TopCat web page, and it's got a list of installation instructions for different operating systems. And as I say, it should be fairly straightforward. There are a few things that can sometimes be tricky, but hopefully there's information there that will get you around that. There is extensive help and documentation for everything in TopCat. So there's a manual you can find on the web page. You can Google for it, and you can look through parts of it. Some of that is tutorial, and a lot of it is reference information. If you're using TopCat and there's something you don't understand, look for this help button on every window. So if you click on that, then it will take you to this help browser, which will tell you about the window that you're looking at, and hopefully you can look through there and find out what's going on. There's also in this help browser a search tool. So if you type in something here, then it will do quite a good job of searching through where that search term appears in the manual, and then you can go and find the relevant section and read that. I'm certainly not expecting anyone to read the manual cover to cover. It's quite big, but if you want to do that, then please go ahead. Okay, so I'll break there and see if there's any questions. Are there any questions at the moment?
Yes, there is one question in chat box.
Uh-huh.
Navya is asking, can TopCat cross match in higher dimensional astrometric space, including proper motions?
Okay, so it can cross match in higher dimensional spaces in the So here's the cross match window. And if I don't choose sky here, I can choose something like a four-dimensional Cartesian match. And in that case, instead of filling in the RN deck here, I fill in four different values and it will work out in four-dimensional Cartesian space which points are close to which other points. So you can do that. If what you want to do is match with proper motions, then the best thing to do really is to take one of your catalogues, calculate where those sources are going to be at the epoch of the second catalogue. So take the catalogue that's got the most accurate proper motions in it, probably GAIA if GAIA is one of them. Work out, use the proper motion propagation functions which are in TopCat. Show what that looks like. So this is the browser for all the functions in the expression language, and we'll look at some of these later. But one of them is this one, epoch prop. So if you've already got columns giving you right ascension, declination, parallax, proper motion, and in RIN deck, and maybe radial velocity as well, then you can create a new column which will give the positions at the epoch of the second catalogue, and then do a normal positional cross match between your propagated positions in one catalogue and the unpropagated positions in the other catalogue. That's probably how you'd approach doing proper motion, working with proper motions when cross matching. But yeah, there are other options as well.
Okay, so there are two more questions. It
Mm-hmm.
is a very basic at a very basic level. And I hope that when you can answer it. That Pratik is asking, sir, as it looks very complicated, should one start learning TopCat for very specific purposes?
Yeah, that's a good question. So I would say, well, hopefully you'll get a kind of idea of what it looks like when I start doing the demonstrations. But I would say the best way to learn it is to take a table that you're kind of interested in and just load it into TopCat and push a few buttons, and then you can see what's there. You can see what the data looks like. You can do some plots. Um, and then if you find out you want to do some cross matching, then find the cross matching window, find the cross matching part of the manual and look at that. Yeah. But kind of once you've got the data in there, then just sort of exploring the user interface is probably a good way to start. But if you've got a particular task that you want to do, then yeah, you can start with looking at the part of the manual that explains that.
Okay. So there is one another question by Tulika. We need to have knowledge of Python and C for using TopCat. Am I right?
Definitely not. No. you don't have to do any programming at all. So the only thing I mentioned C was when you're doing these, when you're calculating these using the expression language. Oh, sorry. So this syntax is strictly speaking Java syntax, which is like C syntax, but you can work out that you need to put A minus B if you want to subtract one thing from another. So no, you don't need to do any programming at all for TopCat. You just need to be able to look at a graphical user interface and point and click at it.
There is interesting question here by ABR. He's saying that I am an amateur astronomer enthusiast learning basic. What kind of projects we can do to kick a start with TopCat learning?
Yeah, okay. I know that it is used, TopCat is used by amateur astronomers, which I'm really happy about. But I don't have a very clear idea of what sorts of things amateur astronomers get up to. So I don't have a very good answer to that. You could try looking up I don't know what amateur astronomy fora there are, but looking at what other amateur astronomers do with TopCat. But otherwise, I'd say just, if there's a source catalog that you're interested in, take it and load it in, and then, have a play around and see what you can do. Sorry, I don't have a better answer for that. But as I say, I'm not very well up on the kind of problems that amateur astronomers need to solve.
Okay, I think that questions are that's all. And I had one or two questions if you
Mhm.
like to ask.
If I
Okay,
may,
so
there is one question by Surendra in the chat yet. We haven't.
okay, so mhm. Yes. So he is asking a beginner in astronomy data analysis, and what would be the best way for students to practice and learn TopCat effectively?
Well, so the script that I'm going to the examples that I'm going to go through after this, there's a script which looks like this, which I think you've got a link to, or you can find the link on the first slide that I gave. You can find it there. So this script is designed to take you through the kinds of things that TopCat can do. And so I'll go through it. So this is probably a good time for me to explain how the rest of this session is going to work. There's this script which has got 5 kind of example science cases in it, which do sensible scientific analysis and perform something that's actually useful based on real data. And each one of them gives you quite detailed information about how you start it up, what buttons you push, what things you fill in, what's going to happen when you do that, what the data looks like. So it'll give you screenshots. So if you want to understand how to actually use it to do to do genuine scientific analysis, and you've got 2 or 3 hours to spare, then going through this script and following along with it should give you a pretty good introduction. Or if you've got less time than that, just do one of the examples and you'll start to get an idea of how to use it. So the way the rest of the session is going to work is I'm going to go through these, and each one will take me, I don't know, 15, 20 minutes or something like that. And I'll explain what I'm doing as I'm doing it, doing the same things that it says in this script. And while I'm doing that, either you can just watch me doing it, or you can, if you've got TopCat installed, you can do exactly the same thing while I'm doing it. It depends how you like to do that sort of thing. If I'm participating in something like this, I usually just prefer to watch someone do it rather than trying to do the same thing myself at the same time, but whichever you prefer. And then when I get to the end of each of those, I'm going to pause for, I don't know, 5 minutes or something and take questions if there are any, at which time you can either kind of start doing that and follow along with the first bit of it, or if you've been trying to follow on before, you can catch up a bit because you might have not done all the things that I've said. Or you can just, have a break or read your email or make a cup of tea or whatever it is. So for a tutorial that will give you a chance to understand certainly not all of what TopCat can do, but quite a lot of what it can do, then working through this script, either watching me doing it or doing it on your own, I would say is quite a good way to to get a handle on lots of the things that it can do and the general sort of way that you can work with it to do scientifically useful things.
Yeah. Yeah, we will do it after a couple of minutes. After taking these few questions are there, and shall we do this? Shall we take these questions, Mark?
Yeah, sure. Actually, I do
Okay.
have, I can see the chat here, so
Yes,
I
yes.
will
You just
read them
take.
out. Right, let's
So,
see.
okay, so here Navya is asking, does it?
Okay, so which Java version is best to install? Pretty much any
Yes, yes.
Java version. Oh, someone's already answered that. Yeah, so Java 8 is fine, but if you've got a later one, that's fine as well. And it's not likely you'll have one before Java 8 because that's pretty old already. Does it do rigorous error analysis to identify what the true matches are after having an initial set of objects that lie within the tolerance value? That's a very good question. The answer is no, it does not. It doesn't do anything clever. If you ask it to do, you tell it exactly what your criteria for matching are, which for instance might just be, I want them to be anything within 1 arcsecond, and it will tell you all the ones that within 1 arcsecond, and that might well not be the right answer. And in fact, one of the examples we'll go on to later on will show you that in action where you don't get the right answer. So you once you've done a cross match, you should definitely look at the results and try and understand what it's telling you, and see whether it's given you an answer that's sensible or an answer that's not sensible. It does. So there are things that some other cross-matching frameworks do, which are more sophisticated. Like, for instance, give you a likelihood that it's a true match by looking at the density of sources near where the match is, and so on. It doesn't do any of that. It does very straightforward, unsophisticated matching. But it does that in a reasonably efficient way. If you want to do more complicated things, then you're going to have to think harder and maybe use other tools. Yeah, it's a good question. Although built-in methods in TOPCAT to statistically test correlations, not much. There's not very sophisticated statistics. The only exception really is you can calculate if you've got a plot in 2 dimensions, it will calculate a correlation coefficient for you. It will do a linear best fit and calculate a correlation coefficient, but it doesn't do anything more sophisticated than that. Okay, when working with large survey catalogues, how do you decide whether it's better to perform cross-matching locally or using remote VO services? If you've got the data locally, then you might as well try it doing it locally. So it comes down mostly to whether the catalogue that you want to match it with is too big to download or too difficult to download. If you're matching 2 catalogues that are small enough, then you can do it within TOPCAT, and that's usually a little bit easier. If you're matching a catalogue which is small enough with another catalogue which is far too big that you couldn't download, then usually you need to use an external service. And the one that I'd start with is the CDS cross-match service, which is this button here, and I'll show you an example of that later, but you can use TAP as well. Right, the internal SAMP hub often fails. Okay, that so SAMP, which I mentioned briefly before, is when TOPCAT can talk to other tools on the desktop. So, for instance, TOPCAT can tell Aladdin to point at a particular position on the sky. When it works, it's neat, but unfortunately, sometimes it doesn't work. And when it doesn't, it's usually quite difficult to diagnose what's going on, because just because when there's 2 programs talking to each other, there's lots of ways that it cannot work properly. So I don't have very good advice for that. I don't think installing a different version will help particularly. One trick that does work or does make a difference is usually if you start TOPCAT up first and then start up other applications like Aladdin, that usually works better than doing it the other way around. But if it doesn't work, I mostly just apologize, and it's not particularly easy to fix.
Okay, so there is question from YouTube Live. So is TOPCAT similar to that of QFITS?
I don't know what QFITS is, sorry. So I can't
Okay.
answer that.
Okay, I think we should start the actual
Okay.
session. Yeah, because time is 6:50.
So as I say, these examples are mostly going to be based on data from Gaia, which I guess many of you will know what it is, but just in case you don't, I'll briefly introduce it. Gaia is an astrometry satellite launched by ESA. It's sitting at L2. Sorry, no, it's not. It was sitting at L2. It had a 10-year mission, and it was finally turned off about this time last year. And its job was to do very accurate measurements of positions and brightnesses of point sources, which are mostly stars in the Milky Way. And it measured about 2 billion of them, complete down to around G equals 20. So yeah, most of those are stars, but it picked up some other point sources as well, like distant QSOs, and also some solar system objects and things like that. And because it was able to, it spins around and twists and observes each point source that it sees multiple times, a few tens of times over its lifetime. And because it keeps track of every time that it's done each of those observations, it can very accurately measure not only the positions of each of those points, but also how they're moving across the sky since last time it saw them. By analyzing those patterns, it can work out the parallax of those objects. Because Gaia was moving with the Earth around the sun, its position was changing every 6 months. It was going around the sun, and so by seeing how much sources were apparently moving, it could get an idea of how far away they were, and it could also work out what the proper motions those sources were, how they were actually moving relative to the solar system. And it did some radial velocity measurements as well. So in principle, it can work out in 3 dimensions what the motions of those stars were, as well as the positions of them very accurately. And it also did photometry in 3 bands down. So the astrometry measurements were in microarc seconds to milliarc seconds, and the photometry was in millimagnitude accuracy. So it can determine brightnesses and variabilities and things like that. It did a little bit of photometry as well, and because it's in space, then it does a very good job of providing a uniform survey across the whole sky. So it's a really, really nice data set to work with. It's been highly successful. There's been many thousands of published papers based on Gaia data so far, and those will keep coming over the next years and decades, I think, with impacts on all areas of astronomy. One nice thing about it is the data is released to everyone at the same time. So even the people working on reducing the data and turning it and doing the processing that turns it into a usable catalog, and that's a very complicated job. They're not allowed to do science work on it, apart from a few slight restrictions, until the whole catalog is released. And then anyone can do science work on it. So, regardless of kind of, what institute you're associated with, or whether you're not associated with an institute at all, you've got as much chance to do good science on Gaia data as anyone else does. The most recent data release was in 2022. That was data release 3, and there's another data release DR4 expected at the end of this year, hopefully. And each of the subsequent data releases works with a longer amount of data, so the values are more accurate, and also has richer data products. And there'll be kind of much more kind of complication in DR4 than there is in DR3, but we'll just be working with DR3 today. Okay, so I explained how the exercises are going to work, so let's go. And by the way, as I say, this I'll go on for an hour or something. If it's getting too complicated for you, or if you get bored, if you have to go and do something else, that's fine. You can drop out. But I'll carry on for as long as people are interested in towards the end of these exercises. So I start off by starting TOPCAT. And the first exercise that I'm going to do is trying to work out, look at membership of a cluster called Messier 4, which is, I think, a globular cluster that Gaia has done observations for. So the first thing I'm going to do is go to the virtual observatory menu. So these this is what TopCat looks like. Down here is a list of tables that I've loaded, which I haven't loaded any so far, and then I load a table and it tells me some information about it there. And then along the top, there's various things that I can do. These ones are plots, and these are different ways of looking at the table. And these buttons, if you hover over them, you'll get a tooltip which says roughly what they do. But you can also look in the menus. All of these toolbar buttons have got appear in the menus as well. So, for instance, in the table data. I'm sorry, the doorbell's just gone. Just give me 1 second. Thank you. Sorry about that. This table data viewer button here also appears down here. So there are different ways just to do the same thing. So in this case, I'm going to look in the VO menu, the virtual observatory menu, and I'm going to use the cone search option. So this opens this cone search window, and this is one which lets me go to a remote service, in this case a Gaia service, and download rows in the source catalog that correspond to the part of the sky that I'm interested in. So because I want Gaia data, I'm going to type in here Gaia DR3. So that then goes off to the VO registry and says, can you tell me, are there services which have data with Gaia DR3 somewhere in the description and which have cone search information? So I could, in principle, choose any of these. The Gaia data is replicated in lots of places. I think this is probably a good choice at the moment. Got this one called Gaia Light Cone, DR3 Light Cone. So then if I've highlighted this, it fills in the base URL for that query here. I don't need to know that, it's just done it. And then I say I want to know about M4. So I type in M4, the name of the object that I'm interested in. If I hit return or push resolve there, then it goes off and queries the sky position of M4. It's actually asking the Simbad service in Strasbourg what that is and fills in the positions there. And I say I want the radius of, what did I say, 0.3 degrees, I think. And hit OK. And off it goes. So this has now loaded me a table. This is what it looks like. It's got rows and columns, and I can browse around those. Here, there's some information about it. It says what it is. It's got 51,000 rows, 26 columns. And a good idea once you've loaded a table is to do a plot of it and see what you can see. So if I click this button here on the sky plotting window, or do the same thing up here in the graphics menu, it will plot me those positions. And so each of these dots is one of those. Is one of those one of the rows in the table. And if I look at that window there, and if I click on one of these, then it will take me to the corresponding row. I'm zooming in and out here using effectively a mouse wheel, but there's other ways of doing it. You can use control drag, and there's some other navigation options that you can see. If you click this question mark button down here, it tells you how to do the navigation and gives you different options for navigating. So it's pretty straightforward to do that. So that's what it looked like on the sky. And you can see there's lots of sources at the position that I said. So probably most of these sources that are actually in this cluster, M4, but a lot of these are going to be background sources as well. And we want to try and work out which are the ones that are actually in M4 and which ones are not. So the next thing I'm going to do is do a different kind of plot. And this one, the plane plotting window, lets me just do a scatter plot. And what I'm going to do now, so if I just push the plot button, it plots the two first columns that are numeric that it can find, which is a plot, but it's not the plot that I want. So I go down here and choose the columns that I'm interested in. And in this case, I'm going to plot proper motion in RA against proper motion in declination. Oh, by the way, I should go to the columns window. So that tells me what columns I've got. And so I can see here, these are the 26 columns that it's given me. And these are the column names, data types, units. So the PMR and PMDEC are in milliarc seconds per year. And it tells me exactly what I've got here. Proper motion in right ascension, J 2016, and so on. So this is useful information if I don't know what it is I'm looking at. So I've done the plot of proper motion in RA and DEC, and so this is a plot in proper motion space, which means that points that are near to each other represent objects which are moving across the sky with the same velocity. And so you can see there's obviously two very distinct subpopulations here. There's this subpopulation here, which is sources which aren't moving very much. So they're not quite at 0, 0. Anything that was sat just here would be not moving across the sky at all from where we are. But there's a lot of these that are moving a little bit, and that's probably to do with our rotation around the center of the galaxy. And then there's these ones here, which have got a much more well-defined proper motion. And so all the objects in this bit of the plot are moving with a similar velocity across the sky, similar proper motion. So what I'm going to do now is click this blob button here and then just draw with the mouse around the region that I'm interested in. Once I've done that, I click the same button again, and it gives me an opportunity to say what I want this subset to be called. So I'm going to call it co-moving and click add subset. So now you can see these are identified in a different color. If I go to the subsets tab in the plot, I can control which of those subsets are plotted. So if I unplot the all one, then those ones go away. If I unplot the co-moving one, those ones go away. On the original plot, I can see now some of these things are blue, which means that they're these co-moving ones, and some of them are red, which means they're not. They're probably not the cluster members. And I can use this button here, which shows me the row subsets for that table. And so the subsets, all tables have one called all, which is all the rows in the subsets, 100% of them. And then I've defined this co-moving one, which has got about half of the sources, and it tells me how many, 25,000 there. So this window manages different subsets that I've defined. I'm going to create one other one. So if I choose this button, create subset complementary, it makes another subset, which is all the ones that are not in this one. It automatically calls it not co-moving, although I can change that name if I want to. So now I've got half of them in the co-moving set and half of them in not co-moving set. If I look back on the subsets window here, you can see there's those two different sets. Oops, and they're annotated down here. So there's lots of different ways you can do plots. By default, you just get the normal scatter plot. But if I go to this form tab, I can plot this information on the sky in different ways. So this gives me various configuration options. So for instance, I can change the size of those blobs. I can make them bigger or smaller. I can change the shape of them, so I can make them like hollow circles. I can change the colors, and I can do lots of different things. There's lots of different configuration I can do here. We'll come to that shading mode later. But another thing I can do is click on this forms button, and this gives me different kinds of plots that I can do based on the same positions. In this case, I'm going to do add sky vector. That adds a new item in this stack here, and that is going to, that's going to let me plot little arrows, or maybe big arrows, for each of these points based on the proper motions that we've got. So I can choose in here delta ln proper motion in RA, and in here proper motion in declination. And then I get an arrow from each of these points in the direction where that thing is moving. Now you can see these arrows are far too long, so I need to make a modification here. And that's because it's identifying each of these proper motion values as a distance in degrees, when actually what it is a measurement in milliarc seconds per year. So I need to scale those arrows to a more sensible size. The easiest way to do that is just to click scaled here, and then that gives it some sort of arbitrary size for each arrow that makes it a kind of a reasonable size to see. And so then I can see what I've got here, which is the blue objects, the ones that are in the co-moving cluster, and so these are ones that are really part of the same cluster. And the reason that the co-moving ones are actual cluster members is because they're formed at the same time, and so they're moving across the sky with the same velocity. All of those have got velocity arrows which are pointing in pretty much the same direction down and to the right, whereas the background sources are pointing all over the places, or maybe they haven't got a proper motion on them at all. And that's really saying exactly the same thing as these sources are in the same region of the proper motion space. Okay,
But
yeah, please.
I have a question here that while doing the scale things, what does it mean? The scale is one or
Okay,
scale
so
is
there's various options here, and if I click degree, then it interprets the values. So it's actually looking at these values, proper motion RA and proper motion index, so -12 and -18. It's interpreting them as -12 degrees, -18 degrees, and so that's the size of the arrow that it's drawing initially. And there's various other options I can get it to interpret those as arc minutes or arc seconds. So that then, gives me shorter arrows because arc seconds are smaller than degrees. But sometimes, I mean, in this case, I don't actually want a number in arc seconds. The value is in milliarc seconds per year. That's what GAIA gives you. And so it's some number which doesn't really map to any particular size that I'm interested in. What I really want is arrows that are kind of the right size, that I can see them all on the screen at once. And that's what scaled does. So it looks at what all the sizes are and picks the scaling that makes them about the right size that I can see them without having arrows that are far too big or far too small. And I can adjust that as well. So this scaling thing here, I can make them bigger or smaller according to taste, either by sliding that or by putting a value into this thingy here. Does that answer the question?
okay. So it is not the amount of the vector, I mean the length, but it is just a direction, right?
Well, no, so it is scaled by the length. So values which are larger in PMRA and PM deck here will have larger arrows, but it applies some sort of arbitrary scaling, but the same scaling to all the points in the picture. So, if that value is too big, then the arrows will be too long to see and you won't be able to tell what's going on. If it's too small, you won't see any arrows at all. So it picks a number to scale all the values by and uses that one. And hopefully that gives you something that's, easy to understand visually.
Okay, thank you.
Okay. So having got that, we now have these two different subsets, the co-moving and not co-moving, and we can do something useful with them. So what I'm going to do now is plot a histogram of parallaxes. So parallax is one of the quantities that Gaia has given me. That's for all the sources. Go to the subsets tab here, and so I can plot moving and not co-moving separately. I can zoom on in one direction in the plot by putting the arrow on this axis, putting the cursor under this axis and doing a zoom, putting the cursor on this axis and doing the zoom. So that lets me zoom in one direction only. So if I do that, I can see that these two populations, the non-co-moving and the co-moving populations, have got very different distributions. The background objects, the green ones here, are quite it's got quite a broad distribution with a peak at somewhere like 0.2 milliarc seconds of parallax, whereas the co-moving ones have got a peak at 0.55 or something like that, and it's more peaked. So what that's telling me is that the average parallax of the sources that are in the M4 cluster is around that 0.55 milliarc seconds. And because the parallax is a proxy for distance, that means I can work out from that information how far away the M4 cluster is. Now, getting distances from parallax is a slightly tricky operation. To a first approximation, you can do it by just inverting it. So 1 divided by 0.55 is corresponds to, I think, about 200, 180 kiloparsecs. If you're going to be inverting parallaxes to get distances, be careful because the statistics can give you trouble. But if the errors on the parallaxes are small, as a rule of thumb, you can just invert them. So what we've done is identified by looking at the proper motions a population on a particular part of the sky that actually corresponds to the cluster we're interested in, look at the parallaxes of those, and then work out the distance to the cluster. All by just kind of looking at plots and looking at sub-selections of the data, and it's not too hard. So yeah, that's a bit of astronomy that we've done just by playing with the data in TOPCAT. So that's the end of the first example. I'm gonna give it 5 minutes or so, and I'm happy to take any questions. And you can either kind of do some more following along than you have, or just take a breather, or make a cup of tea, or whatever you'd like.
So Mark, I have a doubt here in during the selection process of the sources in the like non-promotion, I mean the cluster members or the non-cluster members.
Yep.
So what we did that we selected by hand that okay, so some region is showing that okay, so this is the promotion of the cluster. But while doing the things for publications like okay, so getting the things precisely, so we need that we whether we have selected in a within a circle or within a rectangle or what criteria did we apply it, so those things matters. Yeah.
Yep, that's a very good question. So that it is also possible to do that in TOPCAT as well. So what I did before was click this blob button, which just lets me draw a blob. This button next to it does something a bit more sophisticated, and this lets you draw a shape which is more geometrically well defined. I get some options. So I could draw a polygon there. Let's try choosing a circle. So in this case, I click one point there, and I click another point there. And I go back and click this again, and then it gives me in a couple of formats the algebraic expression for the shape that I've just drawn out. So this is it using TOPCAT's expression language, and this is using ATQL, which is the query language that you use for working with TAP services, which we'll come on to later. But you can see if you want it in a different format, if you want to just write it in a paper algebraically, you can see what's going on here. It's the proper motion array plus this quantity and a circle around there. So yes, you can do that as well. If you want to have something that you can communicate more precisely to other people, you can use this button. And so as well as oh yeah, so if I want to actually create that, I do moving with that.
So can we edit this expression and try to put it like the radius bigger or smaller, like 6.6, and the positions also like X and Y.
Sorry, can you say that again?
So can we, I mean, edit these expressions so that we can put precisely the center of the X and Y and the radius we want during the analysis?
Yeah, so if I choose different value for that, faster. So if I do that and then go to the subsets window, I can see, oops, I can see this cluster subsets that I've just defined, and actually that hasn't. So I'm going to redo that. What it's done, because I already had this other subset defined, is it's tried to work out which ones were in the previous subset and not the other one. So I'm going to just plot all and then redo this. Okay, so circle, and in fact I'll do aligned ellipse just for variety. So this lets you have something which is in which doesn't have to have the same angular size in both directions. All right, so we'll call that one co-moving. So now if I look at this co-moving subset, it's got an expression which is written here. So the one that I did before just kind of kept a note of which of those sources were inside that shape and which ones weren't. But in this case, this is actually the expression which is defining which ones are inside that subset. And so I can so that's what TopCat's using to work out which ones are there and which ones are not. Or you can, make a record of that and write it in paper or something. Is that the answer to the question you're asking?
I was asking whether we can edit it or and make it the
Oh yeah, you can edit it. So once you've got an expression in here, I can double click on that and I can change it to 5.8 if I want. And then this will become updated, I think, automatically. So the ones if you've defined subsets using algebraic expressions, either ones that you've typed in on your own or ones that it's worked out for you by you drawing a shape, then you can edit them just by double clicking on them and typing in. Is that what you had in mind?
yeah, that's what I wanted.
Okay, good.
Thank
Okay, so there's a couple of questions in the chat from Pratik. Yes, the red dot. Well, the red dots which have no arrows. Let's see what they are. So if I show the window here with the data in it, and I click on one of these, so this one's got apparently no arrow, then it takes me to the row in the table which corresponds to that point. And if I look where the proper motions are, right, there's no proper motions for this. So Gaia, depending on what observations it's made, may not be able to calculate proper motions for some of the sources because it doesn't have good enough data or whatever it is. So yeah, in this case, with no arrow, it's because there are null values for the proper motions for those sources. Yeah. Does it mean they could have radial motion? Yes, they could have radial motion. Well, we'll look at that a bit in the next. Well, so in principle, they could have radial motion. I actually think in the Gaia source catalog, there are no sources which have radial motion but no proper motion. I mean, it doesn't mean they don't have that, but then there are none for which that data exists. Although it does use different ways to work out what the radial motions and the proper motions are. So there might be some. I don't think there are. But in any case, that's not necessarily telling you about the physics of what's going on. It's telling you more about the data processing and the fact that the observations that Gaia made, for whatever reason, it maybe they're in too crowded a region to be able to work out their proper motions, or they're too faint to be able to work out their proper motions, or whatever it is. So you can't conclude from the fact that there's no arrow there that the thing's actually not moving, but there isn't a reliable value for it. That's one of the things that subsequent data processing will improve. So by Gaia DR4, if you look at the same source next time there's a data release, because they'll have done more analysis by then, more observations of more analysis of more years observations that have been taken. Maybe this one will have an error by then, and they'll have worked out what the proper motion of that is. Okay, so let's move on to the second example. There's one more question. We show the mean proper motion of the entire group. Well, you can. So one thing you can do is there's this statistics button up here, and this tells you various kinds of statistics for each of the columns in the table. And this column is the mean. So if I look at proper motion in RA, the mean proper motion of all those sources, mean PMRA of all the sources is minus 9.14. I can choose here to calculate that for just one of the subsets. So if I choose the co-moving, then the mean proper motion of the co-moving values is minus 12.5. There's actually another way to do that using the plot. So if I go to the Form tab, I can do add Gaussian. So then this adds a Gaussian plot on top of the histograms. Now the Gaussian, all it does is really fit a mean and a standard deviation to each of the subsets that it's plotting. We just want those two. And let me make them a bit more obvious. And so since these are not very Gaussian curves, I think they're more flat than a Gaussian curve would be. This isn't a very good fit, but it does tell you here what the mean is of the blue ones and what the mean is of the green ones. So you can read it off on the axis down here. But you can also, if you're in this Gaussian tab here, go down and it will read out for you those values. So the mean of the co-moving one, which is exactly where this blue thing hits the axis here, is 0.535. And if I choose here not co-moving, the mean of the non-co-moving ones is 0.34. Sorry, that's a parallax, but you can do the same thing for proper motion in RA and DEC as well. Right, okay, I'll move on to the next example, I think. Let's get rid of some of these windows. So the next example is going to be doing something similar, but in this case, what we're going to do is look for the Hyades cluster. We can't use quite the same way of doing it as we could for the Hyades. And the reason is that the Hyades is the closest cluster to us. And because it's quite close, it extends over quite a large part of the sky, several degrees. And for that reason, it would be too much data to try and download all of the Gaia source catalogue in that part of the sky, in the part of the sky that the Hyades might extend over. So we have to do something clever. What we're going to do this time is use TAP. TAP is the table access protocol. It's one of these VO protocols. And what it does is let you query remote databases using a language called ADQL. ADQL is, you can think of it as just a dialect of SQL, SQL, and SQL is an industry standard way for querying databases, relational databases. And what TAP does is it's conceptually very simple. It just lets you type an ADQL query locally, sends it to a remote server, executes the query there, and sends you the result back. And then TOPCAT can load that in and show you what the result is. So the first thing that we're going to do is identify the service that we want to talk to. So sorry, what I did was click this button here, which is the TAP window, or again, you can go into the VO window, VO menu and click on it here. And it opens this window for me. And the first thing I need to do is tell it which TAP service I want to talk to. Again, I can search on, I could write Gaia DR3 here, but actually rather a lot of services have got some Gaia DR3 data in, so that doesn't help very much. The one that we want, and again, Gaia data is in various different TAP services. So in principle, this could work for different places, but the one I recommend for this is this one. It's just called GAIA, and it's the one that's at ESA, the European Space Agency, and that's the main archive for GAIA data, although it's replicated in different places. So we click that there. This is the URL that we're going to be talking to, and then I just click Use Service, and it will go and give me a window where I can work with data from that server. The first thing it does is go to that service and goes and asks it, okay, what tables have you got? What columns have you got? What information can you tell me about the data holdings? And so here is a list of all the data that it's got there, chopped up into what are known as schemas, but schema is just like a directory of tables. And the one we're interested in today is GAIA DR3. That's the most recent data release. And if I click open on that, then I can see all the tables that are in GAIA DR3, and there's quite a few of them. By the way, if you're using an older version of TOPCAT, then I can't remember what, these might not appear in the same order. So you can search for the table by saying GAIA source if you want, or there's different, or you can just browse until you find it. But the one that we want is GAIA-DR3.GAIA source. If I highlight that, then it tells me over here in this columns tab, what are the columns that are in that table? And that gives me enough information that I can work out what kinds of queries that I want to make. Whoops. And so this is quite similar to the window in TOPCAT, which tells me about data that I've already loaded, but this is about data that I could load if I wanted to. So this is the column names, and there's plenty of them. And again, the units and a human readable description of what each of those columns is. And so the way the TAP window works, once I've got that metadata, is I can use it by writing a query like select top 10 RA deck from GAIA dr3.GAIA source. So if you have come across SQL before, that will make perfect sense to you. If you haven't, then it won't. But basically, this is just a very simple query saying, give me 10 rows of these columns that I've asked for, RA and DEC, from this table that I'm asking for. And if I click run query, it goes off, goes to the service, presents the query, service executes it, sends me back the results, and here it is. And so this is now loaded into TOPCAT, and I can see this 10-row table, which is what I asked for. If you're not familiar with SQL, ADQL, or actually even if you're familiar with SQL but not ADQL, TOPCAT gives you some help in constructing these queries. So one thing you can do is go to this hints tab, which just gives you kind of very quick cheat sheet for how you can write these queries. And it's got some links to some other places you can go as well. So this one, this Gavo ADQL cheat sheet, is quite a good one. It's just like a 2-page document, which gives you some basic examples of how you can talk to a TAP server. But another thing you can do is look at the examples menu down here. And so if I click examples and basic and say columns from table, it will populate this window here with a query which does what I asked it for. So it gets some columns from a table based on the table that I happen to be looking at the time. And so this isn't the query that you want to do, but it kind of it's syntactically correct, and you can play around with it, and you can think, well, I don't want those columns, I want some different columns. So that gives you somewhere to start with rather than just starting with a blank screen and having to come up with a query yourself. And there's a bunch of other kind of queries as well. So this one represents effectively a cone search, but done using TAP. And the other thing in this menu that's worth looking at is these service provided queries. So these basic ones are written into TOPCAT, and TOPCAT says, well, this is the sort of query you might want to do on the data. But the service provided ones are ones that actually come, in this case, from the ESA GAIA server. And so they're written by people who understand the data that's on this particular service and know the kinds of queries that you might want to ask about. So this is a more complex query, which is it's cone search, or I can go to the next one, different sort of cone search, and so on. And in fact, if you want more information about those, then clicking this info button on the right will also take you to a web page, again, provided by whoever's running this service, which will tell you some more information, or may tell you some more information about that query. So those are kind of ways that you can learn to use ADQL without having to kind of start exactly from scratch.
So
Yeah,
Uh,
please.
uh, so I had one question here that there is one option in examples that upload. So does it take the Gaia, I mean, TopCat loaded table, or do we need to upload somewhere from somewhere else?
No, it takes the table from TopCat. So if I give an example, actually, I'm just going to load an example data set from TopCat. This is just a kind of dummy table. It's not very long. So an upload query looks something like, and let's see, let's do the example, trivial upload. It looks like this. So select whatever it is from, and then you give it a special table name, which is tapupload.t3. T3 means the table that appears number 3 in this list. So all this is saying is upload the table that's already loaded in. And so TopCat manages taking that table, sending it to the remote service, and then the remote service can address it under this name, and then it does the query and gets the result back. So if I just do, say, select top 10 from tapupload.t3 and run it, then it will go off and it's the service has ingested that table and just given me the top 10 rows back as another table. So that's how the upload works. Worth saying that not all tap services support upload, but if it appears, if this says something like a value rather than just this panel will tell you whether the service that you're talking to supports uploads or not.
Okay, thank you.
Okay, so that's how the tap window works basically. So let's do something, do what we actually wanted to do with it. Can we cut and paste? Okay, so I've cut and paste this query from the script. What this is saying is, give me. Oh, I'd say one other thing about this window. It's got syntax highlighting. So if I type something that doesn't make sense, that's not syntactically valid, based on the rules of ADQL and also on the columns and the tables that TopCat knows this service has got, then it will highlight this in red, and this thingy here will light up as well. So if I click this button when something's highlighted in red, it will tell me what's wrong. Unresolved identifier, it doesn't know what the column paralat is. But if I put in, if I spell it right, then this thing goes off and I don't have it read anymore. So this gives you an indication of whether you've written something that's correct or not. Doesn't necessarily mean it is correct if you don't get any syntax errors here, but at least you've written something syntactically valid. It's also possible in some cases to write something where you do get an error here, but the service will accept it. So you don't need to trust that too much, but it's definitely a good indication of whether you've made a mistake or not. So the query I'm doing here is select RA-DEC, PMRA, PMDEC, parallax, radial velocity. So these first 6 quantities, position, proper motion, parallax, and radial velocity. That's enough to give me the position in 3 dimensions, because I've got the RA-DEC and parallax, and the motion in 3 dimensions, because I've got proper motion and proper motion in RA and declination, plus the radial velocity. So that's enough information to work out where these things are in 6-dimensional phase space. We have the position and the velocity in 3 dimensions. And I'm also asking for the color in BP minus in B minus R filters, and then this quantity, which is the absolute magnitude. So I'm calculating the absolute magnitude from the observed magnitude, which is this column FOC mean mag in G, and combine it with the parallax in such a way that it scales it so that things that are further away get a larger value and things that are closer get a smaller value. So that gives us, again, not exact, but an estimate for the absolute magnitude of these sources. So we've got color, absolute magnitude, and position in 6-dimensional phase space from this GAIA source catalog. And then I'm asking for sources with parallax greater than 15. So that means sources that are nearby, they've got a high parallax. I think that's more than 66 parsecs or something, or kiloparsecs. Sorry, I should have worked that out. Anyway, sources that are nearby, and also where the parallax over error is greater than 5. So that means there's a small error, it's a large parallax, but the error in parallax is small. So because of the way the data processing works, in some cases you can get values which have got large parallaxes, but they've also got large errors on parallaxes, which means the observation is not very reliable. So these ones have got reliable position determinations. I've put in radial velocity as not null because not all sources have got radial velocity. And so this will give me sources which have got six-dimensional phase space and color and absolute magnitude information. So let's go. Hit run query. Off it goes. I should have hit the run button while I was doing the explanation. I don't think it'll take too long though. I hope. Okay, there we go. So we've got an answer. So it's loaded a new table. It's got 60,000 rows. And well, I can plot it on the sky. It looks like that. So these are, I didn't ask for a particular sky position, so they're all over the place. That's the default projection, but I'm going to go to this axes tab and change the projection. So I look at it on an ITOF projection. So now I can see it in an all sky projection. And so these are all the sources that are nearby with the information that we need. And the Hyades should be in there somewhere, but we don't know which ones they are. And there's a bit of an overdensity here, so that's maybe it, but I'm not sure. So what we're going to do is something similar to what we did before, but in this case, we're not going to look at two-dimensional motion information. We're going to look at three-dimensional motion information. So I'm going to use this button, the cube plot. So this lets me plot values in 3 dimensions. Oh, no, sorry, I need to do something else first. So we've got the information that I asked for, which is enough information to find out motions in 3 dimensions, but that's not actually the motions in 3 dimensions because PMR and PMDEC are not really, well, they're not Cartesian components of the 3D velocity. So what I want to do is calculate from these values what are the 3D Cartesian positions and velocities. I'm going to do it using the expression language, and the function that I need is available in the function browser. So I push this button to find what functions I can find, yeah, it's within these are subcategorized by kinds of function they are. So in the sky part, there's things for working out what distances are between the sky, and there's flux conversions in this one. But the ones I want today are GAIA. So these are astrometry related functions that are particularly well suited for GAIA data. The one I'm going to use now is this one, Astrom UVW. So what this does is take RA-DEC parallax, PMRA, PMDEC, and radial velocity in no coincidence, exactly the form they exist in the GAIA source catalog, and calculate the 3 components of Cartesian velocity from them. So what I need to do is go to the columns window and then click this button, the plus button, and that lets me add a new column based on an expression that I'm going to give it. So I'm going to call the column UVW. The expression is what I've got here in this example. So it's a strom UVW of array DEC PM APM DEC and radial velocity. I'll put the units in. It tells me in the documentation what the units of that are, which are kilometers a second. And hit OK. So now I can see in the columns window, there's this additional quantity here, this additional column UVW, and it tells me what this expression was. And again, I could double click on that and edit the expression if I wanted to. And if I go to the table window, I can see on the end, there's this new column UVW, which, can I see that? So I have trouble with doing this. Oh, there we go. So the value of that is a three vector. So these are the three components of velocity in three Cartesian components of velocity. So now I've got that, I can do this cube plot. So by default in the cube plot, it asks you to put in X, Y, and Z. But if I change this coordinate selector to vector, I can get it to ask me just to put in a single vector. So as long as that's got three components, UVW does, it will plot that three vector in 3 dimensions. By default, the cube plot gives you does that thing where it just plots points by coloring them in rather than doing the density plot. There's a reason for that, but I'll change it so it's density plot, so now I can see what's going on better. And then I can zoom in and out, as I did before, and see what's going on there. Now, the navigation in the 3D plot is a little bit strange. The easiest thing to do is if I can right click or on a Mac control click on one of the points or basically it's on a line of sight through the data, then it will recenter the data on that point. Change the color mapping. So once I've recentered it so that the thing I'm interested in is in the middle, I can zoom again some more and refine that. And if you can see, I'm not sure if it shows up on the zoom, but there's just a slight overdensity here. So there's like a dark blob here. So I'm going to recenter on that again, control click or right click on it. And now that's in the center and I can zoom until that overdensity is visible. And there's some other ways you can do this 3D navigation as well, but that's kind of the easiest thing to do. So now these are pretty much the points in 3 dimensions that I'm interested in. That's the highest over density of points in this velocity, in this 3-dimensional velocity space, and that actually corresponds to the Hyades. It's the most prominent feature in the 3D velocity space because it's the things that are in this data set which are most obviously moving in 3 dimensions in the same way. So now I can do the blob thing again because it works in 3D as well as 2D. And I'll call those Hyades. And so then we have a subset which corresponds to the Hyades. And then if I go back to the all sky plot, and let me just adjust the colors of this a little bit to make it more obvious what's going on. Try that. Make it a bit bigger. So now you can see we've identified some sources which are near that positional overdensity that we saw. And so these are the ones which have the same 3D velocity. And most of these will probably be members of the Hyades. Some of these undoubtedly aren't. They just happen to be in the same region of 3D velocity space. So maybe we can work that out. So the next thing I'm going to do is do a different plot. I'll do a color magnitude plot. So we asked for the color and the calculated value of the absolute magnitude. And so this is an HR diagram. It's upside down. So I'm going to go to the axes tab here. On the axes tab, you can play around with the way things are represented a little bit. So for instance, I could plot some of these axes as logarithmic if I didn't want them to, if I wanted them to be logarithmic rather than linear. But in this case, what I want to do is change the magnitude axis so that instead of going from low to high values, it goes from high to low values because that's how you normally look at these things. So there we've got a kind of familiar color magnitude diagram with a main sequence and a giant branch and so on. And that's for all the sources that are nearby. And then if I go to the subsets tab, I can plot the Hyades on top of those. And you can see there, again, let me change the color mapping. So you can see the ones that we identified, the Hyades, are on a much tighter main sequence than this broad one that corresponds to all the sources that we've got. So let's turn off the background sources. And these are the ones that we're interested in. So it's quite nicely grouped. There are some outliers here, obviously. So let's try and see what's going on with those. Let's turn those off. So again, if we click on these, we can see which ones there are. So most of these are kind of within the range of the positions that we're expecting. I think this one up here. So if I click this one, which is obviously an outlier, it's far from where it looks like the Hyades should be. So this is presumably some sort of interloper, and I could do some cleaning up by getting rid of this one. Did I have something else I was going to do for this? Oh yeah. So something else I can do to investigate these other objects, as well as seeing where it appears on other plots and seeing where it appears in the plot window, is to configure different actions that can happen when I click on these. And these are done using this window here, the activation actions window. And again, it's in, if I go to views, it's on here as well, activation actions. So if I click on this, I get a window which lets me configure different things to happen when I click on a point or click on a row in the table. And what I'm going to do for this one is display hips cutout. So I choose this item and I check the checkbox. What that means is every time I click on one of these points, it will do whatever it says in this panel. And I can look at the help documentation if I want to find out what that is. But what it actually does, let's try it. If I click on one of these points, it takes the sky position, goes off to a remote service, in this case, a one giving DSS to color information, and gives me an image around that part of the sky from this remote server. In this case, so it's giving me a 1 degree field of view. That's much too much. Let's try one arc minute and do it again. Okay, so that's better. So now it's going to DSS and giving me the actual imagery for that point. And so then I can see what the star looks like, and maybe I'll see there's some confusion with another source or something like that. But anyway, it can be interesting to see what those objects look like. At the moment, it gives me data from the DSS survey, but if, for instance, I want something else, there are lots of other surveys I can choose from here. So this is all the different HIPS all sky surveys that are out there, and I can choose, say, infrared, two mass color data. And then if I click on one of those, it will give me instead 2 mass imagery around the same point. So you can investigate by, getting image data. There's lots of other things you can do here. One thing is you can make it talk to other tools on the desktop. So for instance, you've got Aladdin or DS9 loaded with imagery. You can get those tools to point to the sky position that you've identified according to the source that you've clicked on. Okay, so that's the end of that exercise. Again, I'll give you some minutes to recover, and if there's any questions, I'm happy to answer them.
Yeah, it was quite in-depth description of these things.
Yeah.
But I had one question that can we save these DSS images and all while interacting?
Yeah, it's possible. It's not that straightforward. So if I do that, I've got it tells me what I've done here. So every time I click on one, it will give me down here the URL of the image that it's gone and got. This is a FITS file. So I could just take that value and cut and paste it somewhere else. Oh yeah, actually there is another way of doing it. So if I go back to the expressions window, then I think, well, let's use the help because I can't remember what the answer is. Oh yeah, okay. So if I look in this URLs section, there's this function, hips2fits URL. So hips2fits is a service run by CDS in Strasbourg where you give it a position in the sky and some other information. and it gives you back a URL, which is a cutout of a sky survey, a particular HIPS survey that you've specified around the position that you ask for. And so I can use this function here to construct me a URL. I have to give it the ID of the HIPS survey that I'm after. So in this case, it will be 2mass color. I can ask for it in FITS or PNG or JPEG format, and I give it the central position and the field of view and how many pixels I want, and then it will give me the URL that's result. You can do that outside of TOPCAT as well if you go to if you search for HIPS2FITS, and that's a web service that will do the same thing for you directly. This just gives you a bit of a shortcut in constructing the URL that you can use, which is a call to the HIPS2FITS service.
Nice. There is one question in the chat box.
So there's one that said, do you suggest any course to start working on TOPCAT? So yeah, the answer is the script that I'm working from here, which is this one. So that you can find it on GitHub there, or there's links to it on the TOPCAT webpage, so you can find it there if you look for tutorials. Image of star or any astronomical object can be plotted in TOPCAT. Well, so this isn't really plotting it. All this is doing, I mean, TOPCAT's doing a very dumb job here. All it's doing is grabbing it is asking a remote data service, can you give me a square of pixels which corresponds to this part of the sky and corresponds to this sky survey, and then it just presents you the picture. TOPCAT's not doing anything clever. It's just showing you a picture that it's asked for. So if what you really want is sky imagery, you should use a tool which is good with sky imagery, like Aladdin, for instance, or maybe DS9, depending on what sort of thing that you want to do. Okay, if I want to match string arrays for two tables, what should be the operation command? Okay. So we'll do, actually, cross-matching will be the next thing that we cover, but I'll answer that now anyway. So here is the cross-match window, and I said before, this is what it looks like by default. You have sky and you fill in tables that you want to match and the RA index of each of those tables. But you can choose, for instance, sky with errors. So in that case, you have sky with errors, and then you fill in not only the RA index, but you fill in the error column, which is for each table, where there's for instance, a characteristic size of each source, you can fill that in. Or another option you've got is exact value. So in that case, you give it the two tables, and then the matched value column can just be a string or an ID value that matches between the two tables. So if you've got one string, which, like for instance, a source ID, which is going to be the same in two tables, then you could just enter that in here. If you've got, as per the question, three different strings and you want them all to be the same as each other, the easiest thing to do is to use this exact value matching. But in here, you'd write, instead of a single value, like for instance, ID, you could write something like ID1, or if they, and the question says XXX, Y. So you could just do XXX plus YYY plus ZZZ. Because you can write anything in the expression language here. It doesn't have to be just the name of a column. And this is the syntax for joining strings together in the expression language. You just use a plus. So what this would do is, and then you do the same thing in the other one. And so that will give you a single string made out of three strings that you can match between the two tables. That's how you do that. Can I show a tutorial PDS with you? Yes. So the most straightforward way to get it is it's not it. Almost is. Right, here you are. So I'll put this in the chat. So if you go to that URL, you'll see this, which is just the materials for this talk. So TC intro is the slides I was giving at the start, and TC Tuto is the tutorial, which is the script that I've been going through that shows you these examples. There's a version of this which is pretty similar, which is also on the TopCat webpage, so you can find it there as well. But this is just for convenience. And in this data directory is the data files that you download from the services that I'm doing as I go through the exercises. These are here mainly so that if one of the services was broken and I tried to do it, I could download it from here instead. So yeah, here is where you want to go. It's one place to go. You can also find it on the TopCat webpage to find the tutorial materials. Can I explain what HIPS is? Yes, I can do that. Okay, so HIPS it's not a TopCat thing, but it's a virtual observatory thing. And what it is, the easiest way to think of it is HIPS is like Google Earth, but looking up at the sky. So it's a way of storing data which represents imagery for the whole sphere of the sky. In many different ways of looking at it. So there's HIPSes for 2MASS and there's HIPSes for JWST and Euclid and so on. And they're imagery, multi-resolution imagery for the sky that you can look at using various different tools. So TopCat does kind of very basic way of showing you HIPS, which is it can cut out a region in one part of the sky. If I go to, so probably the best example is Aladdin Light. If I search for Aladdin Light and just find the first hit, then so Aladdin Light is a web-based tool which does multiple things, but its kind of basic job is to look at HIPS data from all over the place. So it looks like Google Earth, kind of. You can zoom in and out, and you can zoom in and out over the whole sky. And the reason it works well is because it just downloads data at the resolution that you're looking at the moment. So you can see as I go in further, it downloads a bunch of tiles at higher resolutions so that it can show me the resolution that I'm actually looking at on the screen. And you can see here, I can look at data from lots of different surveys. They're not all present on all parts of the sky. And so I can see, data from all sorts of different surveys. And each of these surveys has got a HIPS, which is a big stack of files somewhere sat on a server, which Aladdin and TopCat and various other tools, including some Python ones, know how to query. So that's what a HIPS is. And you can have a lot of fun exploring with Aladdin Light or Aladdin to look at all that data.
Okay, so shall we move to the another example?
Sure, yeah, let's do that. So we've been going for 2 hours, and I will carry on doing this. But if anyone feels like they've reached their limit of what they're interested in watching, it's absolutely fine to drop out. I won't be offended if you do that because it's a fairly intense tutorial. But congratulations to anyone who's still here. So the next one is going to be about cross-matching. And what we're going to do here is take a data set that I'll download from some Hubble Space Telescope data. Let me just clear out some of these windows. in the region of a cluster called NGC346. There we go. Okay. So the way I'm going to do that is download the data from Visia. Visia is, as you might know, an excellent archive of pretty much all astronomical tables that have been published in the astronomical literature. And there's a Visia web page. Again, it's run from Strasbourg, and you can go to the Visia web page and search for data and download it there, and then you could load it into TopCat. TopCat makes it a bit easier for you if you want to. It's got a Visia load dialog. So if I click on the VO menu and go to Visia catalog service, then this is a dialog that talks directly to the Visia service without me having to go outside to a web browser. So I'm going to type in here NGC346, which is the object I'm interested in. And again, it goes and tells me what the sky position of that is. By default, it just downloads a maximum of 50,000 rows. I happen to know I'm going to need more than that for this one, so I'll put in 100,000. And then the data that I'm interested in is from a paper by an author called Guglielmis. So I type that into the keywords field here, search catalogs, and it'll go off and find all the Visia tables which have got some data in the region of NG346 and have got an author with the name of Guglielmis. And this is the one that I'm interested in. It's called in Visia speak JS166549. I hit OK, and it'll go off to Visia, download the data, and load it into TopCat. It shouldn't take too long. Okay, so we have that data there. I can plot it on the sky, and you can see it looks like 3 overlapping exposures of, I think, the ACS camera on Hubble Space Telescope. And these are the sources in NG346. And there's some other ones around it as well. And what I want to know today is which of these sources have got counterparts in the GAIA source catalog. And there's various ways I can do that. But often the best way to do that, especially if you want to find counterparts in a large external catalog, is to use this thing, which is the CDS cross-match upload window. And again, the work here is not really being done by TopCat. It's taking the data, uploading it to a remote service, which again is run in Strasbourg by CDS, called the XMatch service, which you can use outside of TopCat as well if you want to. But it takes your table, sends it to that service. The service does the cross-matching remotely and then sends you back the results. So the first thing to do is tell it which external data set that I want to cross-match with. There's a bunch here that are listed. In this case, what I want is GAIA DR3 Epoch 2016. There's a few different GAIA ones, but that's the one I want. And it tells me there's 1.8 billion sources in that. And I tell it which of my tables I want to match it with, which is this one, the Guglielmis table. Then it asks me again about the match parameters. In this case, importantly, I'm going to put find mode equals all. So if it's best, it just picks the closest source to each of the uploaded points. But if it's all, it will find all the sources that are within this radius of the uploaded source. So hit go, and off it goes, and it sends those 100,000 rows to Strasbourg, does the match there, and hopefully gives me the result back. So this service will work for well, if you do it via TopCat, arbitrarily large catalogs. It's very fast, so you can do really big matches of this if you need to. And hopefully it's coming back now. Okay, good. So it's created a new table. Here it is. And I can plot that on the sky. It's always a good idea to do a plot of data that you download. Well, let's look at the table itself. So here we are. It's got all those rows and a bunch of columns. The columns are, if I look at them, so the first, I think it's 10. The first 10 columns here are ones from the HST catalogue, and then all the other ones are columns that it's added on from the GAIA catalogue that it did the cross match with. So each of the rows in the result contain one row for an association, with the first 10 columns being the HST data and all the other columns after that being the GAIA data. So if I plot this, I can overplot another data set on the one that I've got by clicking on one of these buttons here. So this gives me another option, and I'll add data from this one. So then I've got to plot each of these rows corresponds to a blue point. But actually what I want to plot is not just the position of the resulting match. What I want to plot is the links that correspond to the associations. So I'm going to do that using this button here. And this gives me not just 2 positions to enter, but 4 positions to enter. So I'll take the match table. And so it'll give me a line between the HST position and the GAIA position. And it's guessed which columns I want to use, but actually it's guessed wrong. Both of these are from the HST catalogue. The GAIA one is actually called this one, RA-DEG, and D-DEG for the GAIA positions. So if I now zoom in, I can see that it's a bit of a mess. I'm going to change the representation of this a bit. So as well as the lines, I'll have some points, and I'll make them a bit bigger so I can see what's going on. So what I can see here, we go out to the outside, it's not so bad. So what I can see here is the red source is the HST source, and then it's found a position in the GAIA source catalogue which corresponds to the same thing. So this one's fine, that's probably a correct association. But if I look at this one, it's a mess. There's one GAIA position which corresponds apparently to 4 different HST positions. And if I look where it's more crowded, it's even worse. There's just like matches all over the place. So these are mostly probably spurious matches. Maybe one of them is right, but almost certainly they aren't all. So what's happened is really just that I've done the match by landing these HST sources, by landing the GAIA sources in a region of the HST catalogue, which is very crowded. And within the 1 arc second that I asked for, there's lots of possible matches, and most of them are wrong. So one thing I could do is just reduce the size, the cross-match radius that I asked for. But it's not really obvious that will get me the right answer because, this one could be right, or this one could be right, or this one could be right. It's not necessarily the closest. So there's something else going on here. I need to be cleverer. What I'm going to do is create a couple of new columns which correspond to the offset between the GAIA position and the HST position. So I go back to the columns window. And I'm going to again create a new column by pushing this plus button. And I'm going to create one column called RA delta. And the expression is going to be the seconds. The difference in arc seconds between the HST position in RA and the GAIA position in RA. And then I'll do the same for declination. So now I've got my 2 extra columns. I can see them in the table if I scroll all the way over to the right. RA delta and dec delta. If I plot them, then hopefully I'll see something interesting. Plot RA delta against dec delta. Do. There we go. So this is a plot of separation in the space which represents separation between the position of a Gaia source and the position of an HST source. And you can see mostly it's kind of scattered, and most of these are random associations that are just spurious and they're wrong. But you can see there's an overdensity here, and these ones are the actual, these ones are the true matches. These correspond to sources which really are in both the HST catalogue and the Gaia catalogue. So I'll do the usual thing and draw a blob. Call it true. And then I can go back to this match window and only plot the true matches, not all of them. And then it's much more obvious what's going on. So here I can see all the associations that are still there are they're only single associations. We haven't got lots and lots of them. Those are the ones that are spurious. These are the ones that are real. And they all correspond to basically the same offset, which again corresponds to that overdensity in the plot that I just showed you. So what's going on here? When I first tried this, I thought, well, maybe because these observations were taken at different epochs, the positions of that whole cluster has moved across the sky by this distance between the Gaia observation and the HST observation. Turns out that's not the case, and it's actually just a difference in calibration of the absolute astrometries of the two data sets. So probably Gaia has got the right calibration, but there's some sort of offset when HST did the observations or recorded the observations or constructed the catalogue. So what I should really do next is take the HST observations and add this, the average of this separation onto those and redo the cross match, and then I'd have kind of a much better result. But you kind of get the idea. That's how it works. So that's one way of doing the cross match. I'll show you another way to do the same thing, because we've already had the question of what's the best way to do cross matches in different cases. And because this is on quite a localized part of the sky, it's actually feasible to download just the Gaia data in around this part of the sky and do the match internally. And so in that case, I can do what I did before and do a cone search. In this case, NGC 346. I think I only want about 0.05 radius this time, maybe. So then I can download the Gaia sources in that part of the sky, overplot a new data set here. So yeah, there's the Gaia sources. And so then I can do a match just between the Gaia sources that I've downloaded in the cone and the original HST sources. And I can do that because both those tables are loaded into TOPCAT internally in TOPCAT using this cross match window here. So I click the match button, choose sky, maximum error 1 arcsecond again. And then I just choose the two tables on a match. So in this case, the original NGC 346 table, the HST data, and the Gaia cone search in that region that I just downloaded. I have to tell it which of the positional columns it guesses. In this case, it's guessed right, but you should check that those are the right things and choose the right kind of match and hit go. And off it will go. In this case, it actually offers to plot it for me. So it's told me that it's created a new matched table here with 23,000 pairs. But if I click this plot result button, it will do that automatically for me. And I can see the same thing that I saw when I did the match using the cross match service before. And again, take the same sort of corrective actions. Okay, so that's the end of the cross match example. So that's been 2 and a bit hours. I think I'll stop there. There is another example, but probably everyone's had enough by now. So I'll take any questions now, and then I'll just wind up if no one else has anything else to say. So thanks for your patience so far. Are there any questions now?
Yes, I have one question.
Mhm.
So regarding this cross matching the in the local tables,
Mhm.
so we have there that based matches and all matches from the each one table, right? So does it take that the radius whatever the maximum error we are giving from one table or and matches in the another table, or it takes in both of them, from both of them?
For this one, and let's go to the documentation because that's a good idea. So I click the help button here, and then it says there's various things, and it says here the match criteria box. And so then here it gives you in detailed exactly what it means for the various things that I'm entering here. But in the case of this one, the sky match, what it means is it will report a match if the length of this line is less than the value you give it. So the distance between here and here is less than 1 arc second, then it will report a match. And if it's more than 1 arc second, then it won't. But if, for instance, you use the sky with errors, where in each catalogue you've not only got RA in a deck, but you've also got an error effective radius of the source in each catalogue, then it does something a bit different, and it explains here exactly what it does in that case.
Okay. So it takes each value from the table one and then start matching with the from in the table two, whatever the data set is there, and then it uses the radius as a 1 arc second, whatever the maximum error we are giving, right?
Well, it behaves as if it does that. It doesn't actually go through each table and match each row in one table with each row in the other, because that would be too slow. But it does something which gives the same result as doing that. You can think of it as doing that.
Okay. So there is one few question
Right.
in the chat box also.
Okay. Right, more than two tables at a time. Yes, there is a possibility of doing that. So the to match button is just in here, but if I go to the joins window up here, then there's various other options as well. So I can match, for instance, three tables against each other. Now, it does get a bit complicated when you're doing this because it's not that obvious what you actually mean by matching three tables against each other. What it does in this case is to find groups of sources which are all within, well, in this case, 1 arc second of each other, which is fine if you've got three catalogues which are all kind of, you expect to see the same sources in them, and they've got big gaps between where there's sources. That it works okay. If you've got a crowded field, it does behave in sometimes surprising ways. And so, for instance, you're matching three catalogues against each other, and there's lots of sources nearby. The gaps between sources in the same catalogue are comparable with the match radius that you're after, then it tends to come up with one great big glob of lots of things all matched together, and it's not very useful. So you can do multi-table matching with more than two tables, but you need to treat it with a bit of care. And if it doesn't do what you want to do, there's a couple of options. So one is the multi-table matching in stilts, which is the command line tool, is a bit more capable. It can do some more configurable things with the matching. So I'd advise you to kind of look at the documentation for that. And if that doesn't suit your purposes, then sophisticated matching, it does what it does reasonably efficiently, but it doesn't necessarily solve all your matching problems. All right, so that was one of those questions. For triple match, how does it decide the central catalog? So TOPCAT doesn't decide a central catalog for triple matching. It treats them all equally and finds groups of sources which are all within the match radius of them of each other. In stilts, there is a mode where you can do multi-table matching, where you tell it which is the central catalogue, and then it does a pair match between the central catalogue and each of the additional catalogues. So yeah, that's one of the things that you've got more control of in stilts than you have in TOPCAT. Okay, so in TOPCAT, when cross-matching large astronomical catalogues of different sky identities, how do you decide between fixed radius matching and probabilistic matching to minimize false associations? Well, that's kind of an easy question to answer as posed, because in TOPCAT, it won't do probabilistic matching for you. It only does fixed radius matching. So if you want to do something that's to do with probabilistic matching, you'll need to use some different software. Whether that's a good idea or not is kind of a judgment call. And really, the best way to answer it is by doing the match, looking at the results, plotting them in the sort of way that I've just shown, and seeing if it looks like it's giving you something sensible, or if it looks like it's giving you a load of spurious matches. You can't always tell by looking, but very often, you can see if it's giving you kind of a big match, a big blob of lots of multiple matches where it looks like there should be only one, or whether it looks like the matches seem to be doing the right thing. But you do need to make some judgment in order to work out whether you think TOPCAT's matching is adequate for you.
Okay, I don't see any other question here.
No. Okay. So yeah, I think that's enough for one day.
Okay. I had one or two general question here.
Oh yeah, sure.
Can we discuss?
Yep.
So I saw that your TopCat has a plus sign in the sort by options, right? But whatever I mean, the version
Oh,
I am using it's not there. I'm using 4.9.
okay, so that's a relatively recent addition. So if you want to see that, you'll have to upgrade to a more recent version. I can't remember exactly when I introduced it, but yeah, if you upgrade, then you should see that plus thing. So that enables you to sort on multiple different columns. Where there's a tie in the first column, then you can choose a different column to resolve things that are equal in one of the columns. Yeah, there's new things get added all the time, so upgrading can help. But I do try and keep
Another
things backwardly compatible. So hopefully, if you learn how to do something in TOPCAT, that shouldn't go away, and it doesn't usually change. But just new things get added on with new releases, and sometimes bugs get fixed as well. So
it was needed because we had to rely with other softwares for that
mhm.
after down.
Okay, yeah.
So another was that while using the stilts, can we plot the figures whatever we are doing it here in the TopCat? Or
Yeah, so you can do all the plotting in stilts that you can do in TopCat. The one issue is that it can be the commands get quite complicated, but it's not so bad because let's see, is this going to work? Let me save one of these tables. So if I do a plot like that, for instance, well, whatever, that's not a very complicated one, but that'll do. What I can do is hit this stilts, go to this stilts control here, and this tells me exactly what command I need to run in order to reproduce the same thing in stilts. So if I do that and and paste it into the shell, then it will produce the same plot directly from stilts, and that's also live. I can zoom and pan, but I can also, if I want to, um, just by writing something like out equals x dot png, I can plot the result to an output file, and then that's a PNG file or a PDF file or whatever that I can do something else with. So yes, you can do all the plotting you can do in TopCat with stilts, and you can get TopCat to help you. So you can construct the plot that you want to do in TopCat, hit the stilts command, and then it'll tell you what this command is, and then you can play around with that later in conjunction with the manual to fiddle around with it and improve it if you want to script that and reproduce it later. And
Nice.
by the way, there is also, and this is another thing that's only in recent versions, a lot of these other windows also have a stilts button up here. So if I do that, it will tell me how to run in stilts the command, which corresponds to what would happen if I pushed the run button here. So TopCat can give you help in constructing stilts command, because there is a bit of a learning curve when it comes to stilts.
Nice. I had one suggestion here. I mean, I was facing a lot of problem while doing the things. While plotting the 2D data in this in TopCat, sometimes I get a quite nice result, and I want to that save it for publications. But there I find that okay, so I can do all the like font and levels, everything I can increase or decrease, but I face problem with the tick sizes. The ticks and the excess ticks are not able to controllable. So that give us problem while saving it and putting it in there.
Yeah, okay. So the only thing that you can do with that at the moment really is if you change the size of the window, then the tick sizes will, correspondingly appear bigger or smaller. So if you've got a great big window, the ticks look tiny. But if your window's not so big and you save it, then the ticks, look bigger.
Because of the export options always takes the window size, the ratio from the window size, right?
Yeah, so if it's a PNG file, then that's the number of pixels that you get. But if it's a PDF file, which is what you'd want for publication, then it's vector output anyway, and so you don't have pixelated. You shouldn't have pixelated annotations and so on. Those fonts will be in their publication quality, even though it's a small window. Does that make sense?
Oh, nice. Okay, so
Okay, I'll
So,
wrap up
yeah.
then. Um, so yeah, if you got this far, I think I had a slide on that. Yeah, if you got that far, well done. It's been quite intense. So thanks very much for your attention. It's been great to talk to an audience of young Indian astronomers, and I wasn't sure how questions and answers were going to work with this many people, because sometimes if there's so many people, people are kind of reluctant to put their hand up. But it's been great to have lots of audience interaction. So I've tried to give you a flavour of the sorts of things that TopCat can do. There's plenty of things that I haven't mentioned, so feel free to play around with it and try and work out how to do different things. It's all documented, as I said. You can find it there. You can go to the web page. Don't forget the help button on the pages. And if you end up using it and you've got questions or there's things that you'd like it to do, or you wish you'd asked something in the session or it's not working, then by all means email me. There's a mailing list which you can send messages to there. But if you'd prefer just to send me a private email, that's absolutely fine as well. It's really useful to get feedback from people who are using the software so that I can find out, what's working for them, what's not, what would be good additions in the future, or what's maybe there, but it's not sufficiently obvious that people can work out how to use it. So yeah, any feedback afterwards, I'm really happy to have. And yeah, thank you very much for your interest. It's been good to do it. Thank you.
Oh, thank you, Mark. So it was quite interesting, and one of our audiences was also saying this that the session was very interesting, And thank you, Tulika, for this comment. And this was our first, online session in this group. And I see that the lot of participants are quite active here. It was around 70 participants in the middle. But yeah, uh, many people, I've got feedback that they want to learn this TopCat and the others softwares, and you come in the astronomy. So it is quite interesting. And thank you, Mark, for giving the detailed